Hello and welcome to this second RadiMation webinar. I hope you can all understand me clearly. If not, please let it know in the chat. Also, another general remark, if you have questions for this webinar, this coming webinar, please post them in the chat, and at the end of the webinar, we will try to answer them best as we can. Today, again, we are here with John de Rooij, a RadiMation expert, and we will be talking about close proximity testing for a magnetic field. One other remark that I have for today is that we are recording this webinar. So yeah, just so that you know, and later on we will make this available on the Raditeq website so you can rewatch this webinar. Now I'm gonna give the floor to Jules.
Thank you. Welcome. The topics that I would like to discuss in this webinar are indeed regarding the close proximity magnetic field testing, is the reason and the purpose why these close proximity tests are being performed, in which standards they are referenced and what the specific details in the standards are described, how the calibration can be done, and of course how the substitution, the actual test, can be performed. And I want to have some conclusion also at the end. Reason and the purpose that these close proximity tests are being performed is that more and more mobile devices with antennas are being used, like mobile phones, laptops, wireless headsets, Internet of Things devices, and also, for example, a metal detector. And those devices, because they are mobile, can become close to other systems. And also, we see an increase in the devices that are using magnetic systems like radio frequency identification systems and near field communication. And also recently we see a lot of wireless charging devices. And especially those devices are generating magnetic fields. The benefit of magnetic fields is that they decrease rapidly with larger distances. And that is why the testing should be done on close proximity, close to the EUT itself. And of course, the general purpose is that we have to verify if the EUT is influenced by the magnetic fields that are generated by other devices. So it is an immunity standard to see if the EUT is being influenced. I first want to discuss two definitions that are often used in these standards. One is the close proximity. And in close proximity, we understand that for frequencies below 26 megahertz, that there is a distance smaller than 50 centimeters. For frequency larger than 26 megahertz, the close proximity is when the distance between two devices is smaller than 20 centimeters. So that's what they specify as being close. Another definition that's often used in the standard is the windowing technique, or windows, and the related window size. And window is the separation of the total area that should be illuminated in different equally sized areas, where one such an area is called a window. And this picture, for example, shows that one side of the EUT is separated in 12 different windows, each with a specific size. And depending on the standard, the size is fluctuating a little bit. The idea is that the immunity test itself is performed on each window, because only a small part of the side of the EUT is illuminated, or the field is generated only for that small area of the EUT, so it has to be repeated for all the areas of the complete side of the EUT. And of course, this should be repeated on all sides of the EUT, not only on the left side of the EUT, but also on the front and the back and the right, and so on. Those terms will return more often in this webinar also, and in the standards. The first standard, and which is as far as I know, the first one that has described this magnetic field test, is the MIL standard 461G test. And specifically, it is the RS101 test, which is the magnetic field from 30 Hertz to 100 kilohertz. And in that standard, it is described that a radiating loop should be used with a diameter of 12 centimeters with 20 windings of specific AWG 12 wire, and that it should be used in combination with a distance that the loop is 5 centimeters separated from the EUT that's being measured. These kind of antennas are provided by several brands and manufacturers, and most of those antennas already have an intrinsic distance separator between the loop and the site that is being tested. So those antennas are meant to be directly not directly held close to directly to the EUT, so that automatically the 5 centimeter distance is used. That is the radiating loop. That's the loop that's generating the magnetic field. There's also a measuring loop, which is used during the calibration of the magnetic field. It is designed to pick up the generated field, measure it with a receiver to verify if the generated field is generated correctly and has the correct amplitude. Those measuring loop is also described in the standard, and for the MIL standard it's a loop of 51 windings of 741 leads wire and so on, with a diameter of 4 centimeters. The standard specifically describes how these loops should be generated. That's also because it's used for the current that's being injected in it, so that it's known which field is being generated. And for the radiating loop, the magnetic flux is specified as being 9.5 times 10 to the power of 7 picotesla per ampere for each ampere that's running through the loop. So in this way, it's defined what the magnetic field is being generated. The window size that is described for the MIL standard 461G is 30 centimeters. So every area of 30 by 30 centimeters should be tested separately. And if a device is larger than 30 centimeters, it should just be tested on multiple windows for that EUT. Another standard that describes the magnetic field testing is the IEC 61000-4-39, and specifically I now referencing the 2017 version of that. And that standard is specified as being the radiated fields in close proximity immunity tests, and it is not only, this standard is not only for magnetic fields, it's also for electrical fields. And multiple frequency ranges are specified in this standard, from 9 to 150 kilohertz for magnetic field, then also from 150 kilohertz to 26 megahertz also for magnetic field. There is no specification for the frequency range for 26 megahertz to 380 megahertz. And from 380 megahertz to 6 gigahertz, there is a specification for an electrical field close proximity tests. However, that is not what I'm going to discuss in this webinar. So we're only focusing on the area from 9 kilohertz to 26 megahertz in this webinar for magnetic field testing. What is also described in this standard is that an EUT, a side or window of an EUT, only has to be tested when that area of the EUT is accessible during intended use. So if it's not physically possible to have a device close to a specific part of the EUT, then that part of the EUT does not need to be tested. For example, an EUT that is intended to be used to be mounted to a wall, the backside of the EUT is not necessary to be tested. Only areas that are normally accessible should be tested. Also, for example, service areas or service parts also do not need to be tested because that is not normally accessible to the end user. Then we have the 9 kilohertz to 150 kilohertz specification for this 61000-4-39 standard. And it specifies that a 12 centimeter loop should be used, and specifically it states that it is preferable to use the loop that is also specified by the MIL standard. It's also using the formulas to calculate the magnetic field for a specific ampere or a specific current that's running through it. And it specifies that a frequency step of 10 kilohertz should be used from 9 kilohertz to 150 kilohertz. So it's really doing a frequency sweep every 10 kHz from 9 kHz up to 150 kHz. In this standard, it's also specified that amplitude modulation should be used, 80% 1 kHz amplitude modulation, and there are several levels specified with different field strengths. For example, level 3 will be a 10 ampere per meter field strength. Depending on the product standards can specify which level should be used. This regulation is based on the current going through the magnetic field loop antenna. And there's a difference between the current method and the power method, which I will discuss later on. There is specified that this window size for this test is 10 centimeters. So every 10 by 10 area of the EUT should be tested according with these specifications and test. And also a 5 centimeter distance should be used from the loop antenna to the outer side of the EUT. So also this 5 centimeter distance is applicable to this verification. Then also the same standard specifies that the frequency range from 150 kHz to 26 MHz should be tested. And there a different loop should be used for this one. This loop antenna is a 10 centimeter loop which has 3 windings of 1 millimeter wire. So that's a smaller loop antenna. The frequency stepping is a little bit different because below 1 MHz testing frequency, 100 kHz frequency steps can be used, and above 1 MHz, a 1 MHz frequency step can be used. Also, the pulse modulation is used instead of AM modulation for the lower frequency band, and it can be 2 Hz pulse modulation or 1 kHz pulse modulation. Also, the levels are different, so they are significantly lower because of the higher frequency range. Also, lower magnetic fields are being tested. This frequency range is using, or it's advised to use, the regulation based on the power injected inside the loop, not being the current flowing through the loop, but the power being injected in the loop. So that's a different technique, a different calibration method, not completely different, but a little bit different settings, but can all be done with RadiMation. And this specification specifies that an 8 centimeter window size should be used, also again with 5 centimeter distance of the loop to the EUT. Then there is also one specific product standard related to medical electrical equipment that is specifying this magnetic close proximity testing, which is the IEC 6061-1-2, also with Amendment 1 at 2020. And this standard is specifically for medical electrical equipment, and it refers for the test setup and for the measurement techniques, it refers to the 61000-4-39. However, in this product standard, it's specified that only 3 specific spot frequencies should be tested. Only 30 kHz, 134.2 kHz, and 14.56 MHz should be tested with different modulations and with different field strengths than there are specified in the 61000-4-39. But only these 3 frequencies should be done. There is no need to do a complete frequency range sweep over the frequency range. However, that's still, of course, possible to do, but the standard doesn't require it. And then the next step is to do the calibration. This is the calibration based on the current. And for this setup, I made a drawing which shows all the components that should be used in this calibration setup. That's the signal generator, the amplifier, then we have the loop antenna itself, which is the left side antenna. Then we have a receiving calibration antenna on the right side, which is connected to the spectrum analyzer. And to measure the current that is flowing through the transmitting loop antenna, we're using a current sensor which is connected to the sensor power meter. And for a sensor power meter in RadiMation, you can also use a spectrum analyzer. So I also did draw a spectrum analyzer on the bottom part of this diagram. The current sensor, of course, has to have a transfer impedance configured for the device. Otherwise, it's not possible to convert the measured power back to the current that's flowing through the loop antenna. For the calibration antenna, it is used for the exact and actual measurement of the magnetic field. And to do an accurate measurement, the magnetic field factor of the calibration antenna should also be specified for that magnetic field antenna. There's also a cable present between the magnetic field calibration antenna and the spectrum analyzer, and that antenna can, that cable can of course also be corrected in the RadiMation software. And the magnetic field factor can also be specified in RadiMation. I will show that later on. The previous slide showed that it's possible to measure the current through the loop antenna with a current sensor. There's also a possibility to use a resistor, a shunt resistor, to measure the current that's going through the loop antenna, and that shunt resistor can then be used in combination with a voltmeter to measure the voltage over the shunt resistor, or it can be used in combination with an oscilloscope to measure the voltage across the resistor. A little bit, the part for measuring the current inside the transmitting loop is a little bit different, but and different equipment should be selected. But these three different methods are available to measure the current. As I already told, is that it is important to have the correct magnetic field factor correction attached to the calibration antenna. And that magnetic field factor should be specified in a correction file in RadiMation. And it should be specified in dB picotesla per microvolt. And these values can be retrieved from the datasheet from the manufacturer of the receiving magnetic field loop antenna, and can be entered inside a correction file in RadiMation, where the correction file is just a frequency column and a correction column, which includes the correct values expressed in dB picotesla per microvolt. And then in RadiMation, it can be attached to the magnetic field factor correction file of the antenna device driver. And in the screenshot, you can see that it is the third correction file that can be selected for the antenna. Then that is the setup of the equipment that's all needed. To actually perform the calibration itself using that equipment, in RadiMation, we can go to the calibration menu, the system calibration menu, and then to radiated immunity and the MIL standard calibration. And then this configuration window is shown where all the settings for the calibration can be performed, can be configured. Of course, the frequency range can be specified, the step frequency can be set, the test level can be specified to be used, the tolerance, and on this area here, the measuring device can be specified, and several methods, one or more methods can be selected. The calibration method is selected to be signal generator, because in this setup we don't have a coupler, we don't have a 4-power meter. The complete regulation is done on the current. So the calibration method is set to be the signal generator level. There are different magnetic field units that can be configured in RadiMation. It can, for example, be selected, the magnetic field can be expressed in dB picotesla, in dB microampere per meter, or in ampere per meter. The configuration of the unit can be selected in the unit configuration. If we go back one slide, this is the previous slide. Here we have the units button, and in this units button, you can select which unit should be used for the magnetic field. And then we have the measuring device, and the measuring device is just selecting which set of equipment we are using to measure the current. And that can just be the power meter and current sensor combination, it can be the multimeter and the resistor combination, or it can be the oscilloscope and the resistor combination. And depending on the equipment that is being used during the calibration, the correct measurement device should be selected. And then the calibration is started, and basically it is just increasing the signal generator power. It measures the analyzer, which is connected to the magnetic field measurement antenna. It determines the measured field, and if the measured field is within the regulation, then it stores the measurement of the current in the calibration file, and it continues to the next frequency. If the regulation of the magnetic field is of course not within the toleration, it adjusts the signal generator power to generate more or less power, and thus more or less current through the loop antenna, and it regulates to the desired magnetic field strength. And every time when it is reached the desired magnetic field strength, it stores the current related to that magnetic field strength in the calibration file. To perform a substitution using this current method is using this set of equipment. It's a little bit simpler because the receiving part is not present anymore, because instead of the receiving loop antenna, we now position the transmitting loop close to the EUT. And of course, this can also be done with the resistor, with the multimeter, and with the resistor and the oscilloscope combination instead of the current sensor and the sensor power meter combination. Perform the substitution in RadiMation. From the tests menu, the radiated immunity menu can be selected, and multi-band can then be selected, and then this configuration window is shown with all the relevant settings for the magnetic field substitution test. Frequency range can be set, the dwell time can be set, which modulation, the frequency change mode that can be used can be set, the modulation that should be used in this test can be set. And an important part is the test level configuration. The test level configuration allows you to select the calibration file. And this calibration file is the result of the calibration file, that is the output of the calibration that is performed beforehand. Of course, we can also specify the field test level that should be generated, and in this case it will be 3 amps per meter, and that can be a fixed value over the complete frequency range, or it can be a variable field strength depending on the frequency range. And the leveling method that is being used can be selected in this area, where again you can select to use a multimeter and a resistor, the power meter and the current sensor, or the oscilloscope and the resistor combination, depending on which equipment is being used during the substitution setup. And then the actual substitution measurement is just looking up the required current from the calibration file. It increases the signal power, while it also is measuring the current. And then as soon as the desired current for the requested field strength, magnetic field strength, is available, we start the dwell time, we wait until the dwell time is finished, and then we continue to the next frequency. And then every frequency is tested until all frequencies are tested, and then the test is finished. So that's basically how the substitution test for the current measurement is working. This is used or specified for the 9 kHz to 150 kHz standard for 61004-39. For the higher frequency range, the power method is being advised to use. And we see that we are using a different setup for this measurement. In this situation, we are using the signal generator, an amplifier, and then at the output of the amplifier, a coupler is connected with a forward power meter and optionally a reflected power meter. And the output of the coupler is connected to the transmitting magnetic field loop again. Very often, an attenuator is included between the coupler and the magnetic transmitting loop to convert differences in impedances between the amplifier and the coupler and the transmitting loop. So an impedance matching is very often advised to be used. It can be a coupler or a specific matching network, which is also provided with a lot of antennas that can be purchased. Again, during the calibration, of course, we have to measure the generated field again by using the calibration antenna, which is connected to the spectrum analyzer. To perform this calibration, we again can select from the calibration menu the system calibration, radiated immunity, and then the middle standard calibration, which is just the same configuration window as during the current calibration setup. However, in this configuration, we select as measuring device none, because there is no current measuring device, and we select forward power or optionally net power as being the calibration method, because those forward power and net power settings identify that these coupler and power meter combinations should be used for measuring the power that's being injected in the magnetic loop antenna. So calibration method is forward or net power. Again, the magnetic field unit can be configured as desired. The measuring device should be set to none. And then again, the calibration loop is relatively simple. We increase the signal generated power. We measure the analyzer measurement that's connected to the magnetic field receiving loop. Based on that, we calculate the magnetic field that's being generated, and if that is within the regulation tolerance, then the magnetic field value and the power that's being generated out of the amplifier, the forward power or the net power, is stored in the calibration file. And we continue to the next frequency. When all frequencies are tested, we thus have a table of magnetic field strengths that are being generated related to the forward power or the net power that's being used to generate that magnetic field. Substitution test for this power method is more or less the same as what you can expect. The receiving part with the receiving loop and the spectrum analyzer is not needed anymore. You only have to hold the magnetic loop close to the EUT at a 5 centimeter distance. And then during the substitution, we are generating the same forward power as was specified during the calibration again. And then the same magnetic field will be generated. Again, in RadiMation, the tests menu can be selected with radiated immunity and then a multi-band test. And in this configuration, I specified 2 different bands. One from 150 kHz to 1 MHz using a 10 kHz, using a 100 kHz step, and one band from 1 MHz to 26 MHz using a 1 MHz step. This is the 1 MHz step. Depending on the modulation requirements, the same or different modulations can be used. And again, also the test level configuration is important in this part because it specifies how the measurement and how the regulation of the power should be done. In this case, it's the same configuration window. We again can select the calibration file, which was the result of the calibration setup. We can specify the test level that should be specified. In this case, it's 0.3 ampere per meter or 300 milliamperes per meter. And the leveling method is now not based on current, but it's based on forward power or net power. And again, during the substitution, we use the calibration file. We look up the required power for a specific field strength that should be generated. That is not necessarily the field strength that is calibrated itself. So it is possible to calibrate on 1 ampere per meter and then recalculate it to 300 milliampere per meter. RadiMation knows how to correct the power for that. The signal power is then leveled up to the desired power. The power is measured, and if the correct power is regulated and within the tolerance that's specified, the dwell time is started. And then at the end of the dwell time, the next frequency is started, and so on. And all frequencies are stepped through after each other. And of course, during the substitution test, an overview of the test is being shown in RadiMation. The graphs can be shown of the power that's being regulated. The monitoring with AD converters and EUT monitoring can be done to see if your device is influenced. So all that standard immunity test results are also available in this magnetic field test. We did create some application notes that describe these tests in detail, and those application notes are available on our RadiWiki website. which is available at wiki.radimation.com. Application note 138 describes how to perform a magnetic field close proximity test. Application note 139 describes how to do the magnetic field close proximity test using 4 power leveling. So that's the power method that I described. Those 2 application notes is what I now explained briefly in this webinar. There is an additional application note available, which is 130, which describes how to perform a closed loop magnetic field test, because it's also possible to do a closed loop regulation of the magnetic field. And then no calibration is needed because it's primarily based on the current flowing through the loop antenna itself. So it can be a calibration-less test. And that's already how simple it is to do a magnetic field close proximity loop test in RadiMation. And magnetic field testing, that is the primarily idea to remember. A magnetic field test is just a regulation of the current flowing through the transmitting loop antenna. And there is a relation between the current flowing through the loop antenna and the magnetic field that's being generated. But it all comes back to measuring and regulating the current flowing through the loop. RadiMation does support different methods for measuring the current. So it can be a current sensor in combination with the sensor power meter. It can be a shunt resistor in combination with the oscilloscope or a multimeter. RadiMation is able to use all those different setups to regulate the magnetic field test. And also we are flexible enough to adjust to the applicable standards. It doesn't matter if you have to complete frequency range or only a specific spot frequency that should be tested. Every band can also be a single frequency that's being tested. And also different modulation requirements can be configured, different dwell times can be configured, test levels can be configured themselves. So we are flexible enough to perform this magnetic field test also with different specifications if they are described in different standards. And I did not show it, but the multi-band immunity test module in RadiMation also allows you to add limitations on the power and on the current and on the magnetic field. And we can also measure the values and show them in the graphs. So limitations on different units, different magnitudes like power and current are still possible. It's just an addition of additional test levels that can be configured in the test itself. But maybe that's a nice topic for the next time. And what I conclude is RadiMation is fully capable of performing close proximity magnetic field tests according to your standard. And I know that already more than 15 years ago, we implemented the MIL standard 461 test, the RS101, which is primarily used to do these kind of tests. And I'm very confident that RadiMation is able to do all these kind of tests. So that's the short explanation.
Yeah, thank you very much, Sean, for this webinar. Yeah, now we have time for some questions. I see that we already got one, but yeah, feel free to put them in the chat now so that we can discuss them. If you have questions later, you can also, of course, mail us at marketing Raditeq or RadiMation support at raditeq.com. And we can also handle them later. So the first question that we have is, where do you place the current probe or the shunt? Is it close to the magnetic field loop or to the amplifier? Do you have different results between the field sensor and the shunt starting at something about 100 kilohertz because of the cable losses and the captivity coupling?
The cable losses should not make a lot of difference because it's all low frequency. So I do not expect that a lot of cable losses have influence. The, what did they say? The impedance matching? No. The inductive coupling can have some effect indeed. Most accurate is, of course, to have the shunt resistor and the current sensor as close as possible to the magnetic field transmitting loop. because that's the best point to measure it, and the farthest and the latest point. So as close as possible to the magnetic closed loop is the best in my opinion.
Okay. Okay, so that's a clear answer. I
Yeah.
think it's as close as possible to the loop. Okay, I see that there's no further questions, but we'll yeah, wait a little bit longer. I also want to ask you to please fill in our survey, because we're trying to improve ourselves and do things better each time. I'll put a link in the chat where you can find the survey. It's just 4 short questions and an open one. If you don't want to fill in the open question, please just don't do it and just fill in the other one, so that we have a little bit of an understanding on how well we are doing with these webinars. I also will join or add a link to the following webinar, which will be about the basics of report generation in well, it's already on the screen, but I'll also add the link in the chat right now, so that you can register for the next webinar as well. This is more a little bit more basic webinar, and not a lot into real standards, but more into functionalities of RadiMation itself.
The next webinar that we're planning is indeed for the entry-level use of how to use the report generator, how to create templates, which technique is used to generate the reports, and what can be done and what can be achieved with this. Primarily just as a starter for using the report generator. The report generator is a very advanced and powerful tool in RadiMation. There's a lot to discuss. This is really the basics and the beginnings.
The basics. Yeah, so that's basically it. I don't see any questions yet. I'll leave the webinar open for a bit, so you can still post your questions, and we can answer them later. Thank you for your time and for your presence here.
Yeah.
Also, thank you, Sean. And hopefully we'll see you in the next webinar.
Thank you.
Thank
Bye.
you. Bye.